Um, okay, so first of all, can you see my mouse? Is that okay? Hello? Anybody there?
Yes, we can see it.
Okay, good. So I'm going to give a sort of overview of some of the developments in uranium telluride. Of course, the field has gotten quite expansive, so it's quite hard to catch everything, obviously, but I'll try to catch some of the key issues, at least from our viewpoint, and what we think is important to consider. In particular, advances in quote unquote sample quality and experiments on different generations of samples, as well as experiments on the same generations of samples that don't quite agree with each other. So before I continue, I'll just thank my collaborators, which this list is growing and growing, of course. But I'd say nearly all of my group is working on this project still, in one way or another. And then some great collaborations I've developed over the years, not only on this material, but on others, but we've done some really nice experiments, and won't run through everyone, but theory and experiment, STM, particular Seamus, who's in the audience I see, and I was able to zip through your talk very quickly to make sure I heard some of the key points. So I'll try to address any questions, and please ask me questions if you think of something along the way, and if I can hear you, I'll try to answer. Okay. So this is I wouldn't say it's an old story now, but it's going on 6 years since Sheng's first discovery of this material. Just for nostalgic purposes, this is the actual first resistivity measured, and you can see it actually goes to 0. So that's a real superconductor, unlike some other things we know about these days. You know, this was quickly reproduced, which was quite nice, by the Aoki group in Japan, and then the Grenoble group quickly joined in with Aoki's collaboration. And since then, there's been, of course, several other groups that have synthesized crystals and done experiments and so on. So, you know, one thing I'll say off the bat is that it's really nice to see reproducibility in this subfield, in particular on the crystal quality, crystalline properties, and the different experiments on same and different crystals. So there's, of course, differences, which is sort of the focus of the talk today. But it's really nice to see, you know, different groups grow crystals in obviously different ways, but get basically the same thing. And that goes from CBT crystals to salt flux, etc. So that actually helps us quite a bit and allows us to do quite a lot of good research in a very short time. This was a slide I showed at the March meeting just back a few months ago, just highlighting some of the recent developments that literally appeared during that week of the meeting, both from our group and some other groups. Some really exciting stuff, I would say, in particular, some of the high field work that came out of Nick's group, looking at the angle dependence, as well as the Cambridge group, looking at the high field phases, which are obviously very interesting. But also some tunneling work from our own group, and of course from Seamus, NVIDIA, and so on that appeared recently. So it's quite nice to see some really in-depth studies starting to appear. This is an evolving story still, but it's actually quite a long story, and it goes back to the 60s. This is not a new material. It's just that previous studies had not been able to observe superconductivity until Sheng's observation back in 2018. And if you look at the old literature, it actually is possibly already apparent that one of the reasons is because the crystal growth is a bit sensitive. And so if you look at, I'm sorry, I guess I have a sequence here. Well, I'll get into that. But if you look at some of the old literature, they already talk about just changing the knob of temperature on the furnace to get slightly different stoichiometries and so on. So there's a lot of issues here that you have to consider when you compare different data. But as I said, if you grow the crystals in the right way and you get superconducting samples, for example, the properties on the whole are quite reproducible. You know, we're arguing about lots of details, but I think the general picture is moving in the same direction. Okay, so I think this has been covered, but I'll briefly go through it. This is a condo system, heavy fermion system with the telltale resistivity that slightly rises and then drops below some coherence temperature, thought to be due to the onset of screening from the conduction electrons. It has an anisotropic magnetization that's much like the other uranium superconducting systems. That shows some Curie-Weiss-like behavior at higher temperatures, but then there's a transition in the condo state to something slightly different, and in fact, some maximums in B-axis susceptibility and so on. And this was known from many years ago, actually, so that's nothing new. The crystal growth itself, which is a hot topic these days, it was already known, of course, from the discovery of the superconductivity that if you grow these crystals in slightly different ways, even with chemical vapor transport, even with the same furnace, same materials, you just change the temperature and you get different quality crystals. And so if you're interested, Cheng made a Jove video article if you want to watch that. That's from several years ago, before the advent of flux growth crystals that superconduct. Back then he was comparing just flux growth crystals that did not superconduct to vapor transport crystals that did. And from the Aoki's first paper that reproduced our work, it's also apparent that you can slightly change the growth parameters and get superconducting crystals and not superconducting. So this is nothing new. And as I said, if you look at the old literature, you can already see, for instance, in the 70s, this is this Russian paper, we're just tuning the growth temperature. Actually, there's a span of temperature range where they claim to grow UTe2 the right phase, but then nearby there's other phases that form. And so you have to be very careful about this. I think I made a slide. Oh yeah, I'll get to a slide about the other phases of uranium tellurium that we constantly worry about, actually. I also note right here, and I'll get back to this later in the talk, that the magical molten salt flux is great. It's a great development by the Haga group. But in fact, you can grow crystals with a self flux, which is just tellurium, and get superconducting samples. So actually, we first reported that in this recent paper on thermal conductivity. So molten salt is nothing special. It's just a way to control the stoichiometry that you need to get superconducting crystals that reach up to about 2.1 Kelvin. Okay. The growth, there's different ways to grow these crystals. So far, the vapor transport growth, and as I said, you can tune this temperature and you can get quite different results, at least in the low temperature properties. Or you can use a flux growth, which several groups now have reproduced using sodium chloride, potassium chloride flux with a stoichiometry that's slightly uranium deficient to get superconducting samples. And this has been reproduced even by our own groups as well. And so in fact, if you look at the morphology of the crystals, I think this is quite common. You tend to grow quite large crystals with vapor transport. You can see these nice big crystals here that seem to show nice facets that correspond to the orthorhombic crystal structure. And salt flux tends to give you these more needle-like shaped crystals. So depending on what experiment you're doing, some of these can be advantageous or disadvantageous in just in the shape, of course. So the resistivity, you can see, for instance, this was the Cheng's paper comparing flux growth tellurium flux growth and vapor transport growth, showing that you can get this quite large variation in the low temperature resistivity. But at high temperatures, things are pretty much the same. So it's really a subtle difference. And that's kind of the key, one key message, I would say, is very interesting. You just tune the knob of temperature on the furnace and you get superconducting, non-superconducting crystals. So it's a very subtle, sensitive thing. And as has been mentioned by many people, I think it's probably due to the vacancy count of uranium. That's the likely culprit, but it's at the less than % level. It's a very small effect. And to this day, I'm not aware of a very in-depth or systematic study that's characterized that systematically to show that the count of uranium vacancies corresponds systematically to some property. There's indirect studies, of course, and I'll touch on this. Okay. For example, you have to be a bit careful when you compare the so-called RRR value of crystals. Just a word of warning. So, sorry if I go back one. There's lots of RRRs compared here, for instance, from 50 to 1000 in this in the Paga paper that reported the salt flux crystals. You have to ask how do you define this RRR, because a factor of 2 means a big deal if you're talking about 500 or 1000. And so you have to be careful about how this is actually analyzed. And just to show you an example, if you fit in different ranges of t squared, you'll get, you can get quite large factors that are the zero resistivity. So TC is perhaps a better measure, but even then you have to be careful about resistivity. We've seen lots of times that 2 Kelvin resistivity signatures of superconductivity do not necessarily correspond to the bulk signature measured in heat capacity. It could be a bit lower. So systematics matter. Okay, so this is the example of 60 versus 80. That's not a big deal. But if you're comparing apples to apples, then you can talk about something meaningful. If you're not, then you cannot. So this is from Nick's group, actually a student, Gisela, who compiled a bunch of data from their own samples. So they analyzed the resistive TC and the RRR in the same way in all these crystals. And these are salt flux crystals with varying starting ratios. And this is, just meant to show you that this is a scatter plot, okay? So RRR is ranging from 60 to over 100, and the TC, is all over the place. There may be some trend you can probably draw, but I would say there's many anomalies in this plot. So we're still working on this. It's just tedious. You have to really characterize these carefully using heat capacity and so on to really get a feeling for what's controlling what. But that's the situation at the current day. Okay, the morphology doesn't seem to change. This is again from Nick's group in the salt flux crystals. Maybe they seem a little bit smaller on the lower tellurium rich end versus higher, but basically they're always needles. And then just this word about uranium and tellurium. There are many phases, and just look at the phase diagram of tellurium to uranium, and you can see that UTe2 is this line compound, well, not line compound, but it has a width of formation almost to the melting point. And there's nearby phases, so you can easily get other phases in a lot of these growths, and you have to be careful. And it's been reported in salt flux crystals that there are intergrowths, it seems, at least on the surface, of some of the other phases. And I just quickly went through the literature to sort of point out the different ground states or magnetic states that are seen in these crystals. So ferromagnet, antiferromagnet, etc., metals, insulators. Uranium tellurium 1, for instance, can really fool you. It's a metal, and it has a 100 Kelvin ferromagnetic transition. So if someone shows you susceptibility of a high TC crystal grown by salt flux, I would urge you to ask them, what does susceptibility look like at 10 kiloerstud, not measured in 1 Tesla? And if you see signatures of this, you have to worry what kind of contaminant phases might be in these crystals. So just a word of warning about comparing things. Okay, I'm not going to go through this. This is just all the data. I was talking about these other phases. This UTe, for instance, looks a lot like UTe2, right? It's metallic and so on. Okay. All right, so UTe2, it's this dimensionality question is of course important. And we first studied this just by doing very careful transport measurements. And even from here, you can already see that the what was first reported, the A and B axis resistivities are about a factor of 2 different, but they look nominally similar in temperature dependence. When you measure C-axis resistivity, there's something quite interesting that appears, and it's this metallic behavior that has a peak at much lower temperature than the A and B counterparts. And we're still studying this. This is quite interesting. I think this has it holds some secrets to the electronic structure and perhaps some of the correlated phenomena that happens in this material, perhaps even to do with magnetism.
JP, just to ask a question to get the discussion going.
Yeah.
What happens to these resistivity curves in the high field limit? Do they change a lot?
Yeah, they do change. There's a paper by the Grenoble group that looks at the 3 resistivities in high fields, and you can see how there's a magnetoresistance, and it's quite complicated. It depends on which direction of current, which direction of field. There's 9 permutations of that. So
But
yeah.
Does the apparent Kondo effect still get to occur at, say, the 30-degree angle to the B axis? Do you see that?
Yeah, I believe so. I think the Kondo peak kind of moves up with magnetic field and high fields. I don't have that data here, but yeah, as I said, it depends on what the field direction is and what transport direction you're looking at. Okay. So again, just comparing properties for different types of crystal growth. This, in hindsight, the first observations we made of the specific heat transition, alerted us to the fact that there was this huge residual component of the heat capacity, which in early versions of the paper we actually labeled as gamma over 2, because we were very excited thinking this might be the long sought polarized helium 3 phase. But we quickly realized by doing thermal transport that there was no itinerant states down there. So that didn't seem to make sense. And then with further refinement of crystal growth and increasing TC, this residual term has shrunk. And so you can see it's nice work by the Los Alamos group, where this is all vapor transport, where you increase TC and you can see that this residual value actually decreases. And in the latest experiments on the highest TC samples, it seems to go to very small value, maybe 5 millijoules or so. Another word of warning that these are all extrapolations, as you can see, and if you actually do the measurements to lowest temperatures, there's always an upturn below a few hundred millikelvin. And as far as I'm concerned, this is unsolved. There is probably some component of a nuclear quadrupole shock key giving you an upturn, but it's not completely consistent with that. For instance, if you actually try to fit that data and get a splitting, the splitting is, I think, something like 50, I forget exact, 50 or 100 millikelvin. It's quite large. It's too large to be a nuclear shock key alone. So, I don't think that affects the fact that this is definitely going down, but there's some physics down there that's not well understood. And so just to show you again, salt flux versus, you can make crystals that are self flux and they show beautiful transitions at 2 Kelvin, very low residual heat capacity, etc. So the flux doesn't necessarily matter. It seems to be the stoichiometry that you start with when you grow. Okay, Here's a plot that was published a couple of years ago by Oki, and it's probably been updated since, but this is the best I could find with the most up-to-date data, including the highest TC samples and the lowest residual heat capacity. I don't want to call it gamma because I don't think it's an electronic heat capacity. It definitely doesn't show itinerant conduction, but it's a residual heat capacity nonetheless, and it seems to scale with TC. Okay, why? I don't know. And then, as I said, if you look at the lowest temperature data, you can see that there's always upturns that appear below 200 millik or so, and that's also true in the highest TC samples. You just seem to have to go to a little bit lower temperatures to see it. We're trying to do a systematic study of that, but it's not clear. It's not easy. It requires a lot of division bridge time. Okay. So NMR has been an evolving story. I think I counted recently, there's probably 10 or 12 papers, mostly by the same group. Starting from our own work with a collaboration with Iowa State, with Furukawa's group, showing that there was no discernible night shift change through TC. And just to dispel any worries about the strontium ruthenate saga, this is the in situ measurement showing the frequency change at TC, so there's no heating here. This is real data. And then there's been some more refined measurements as we go along, and the most recent data that I've seen, at least from the Aoki group, shows that there is a change in the night shift that amounts to a few percent change. Okay, so it's and they claim to see it in all three directions. I don't want to be skeptic here, but I would just say that night shift, NMR is a surface sensitive measurement. It's an RF measurement, and so you have to wonder if there's claims of surface phases and so on. How does that affect the interpretation of this data? And furthermore, measuring NMR in a superconductor is a long known challenge. Okay, so there are claims from these results. For instance, they claim this is only consistent with a fully gapped superconducting state, and so I would not tend to agree with that result unless we do further experiments to really understand the effect of surface states and so on. The penetration depth is, of course, also a traditional experiment to study the gap structure. And with my colleague Steve Onlaga down here, early on we did penetration depth measurements using his microwave impedance measurements, showing a nice quadratic temperature dependence on the two samples shown here, which is certainly consistent with a point node gap structure. These were on the first generation samples with 1.6 Kelvin TC. Since then, there's been further work by the Shibayuchi group on higher TC samples, and they see basically the same thing. There's some slight difference in power laws, but they're all pretty close to T squared. And the interesting thing here is that the Shibayuchi group measured penetration depth with their coils pointed in all three crystallographic directions to apply field in the three different directions. And they see T squared in all directions. So this actually drove them to conclude that based on this observation, that there should be some component of a point node in all directions, which would mean it's inconsistent with sort of a single point node or single pair of point nodes, for instance, in this B3U structure shown here. So this conclusion was consistent with a multi-component order. And I should say that Steve Onlager's more recent measurements confirm this. So they see the same thing. It's a quite different experiment, but they see a quadratic temperature dependence in all field orientations. Okay, so I would say that there's a question about how the microwave penetration depth measurements are affected by surface states. And so I think this is an open area for both theory and experiment to investigate. Okay. Now, Kerr effect. Okay, so the moment you've all been waiting for now. So, okay, well, this is I think this has been talked about in many papers now. So the original work that was in our paper, collaborating with Aaron Kapitolnik's group, showed a spontaneous Kerr effect measured in these samples. And together with the observation of a double TC and the heat capacity, we claimed that this was evidence for multi-component ordering. In more recent work by the Los Alamos group, Sean Thomas, they repeated the Kerr effect experiments using a slightly different technique. So they use a laser heating technique where they basically collect all these data points by heating the sample and cooling, heating and cooling, heating and cooling with a laser pulse and measuring the Kerr response. With admittedly by them a slightly less resolution than Aaron's setup. But nevertheless, within the envelope that's claimed by the Kapitolnik group, they don't see any Kerr effect in samples. And just to note, this is both, I don't know if this is the data per se, but this is, oh yeah, sorry. This is both in salt flux crystals and vapor transport crystals. So both generations. And I haven't talked to Aaron lately, but he was certainly interested in trying to reproduce his experiments in higher TC samples. When you apply a field, this is quite interesting, and there's a few papers by Aaron's group with us studying the Kerr effect as you cool in a field and then turn the field off. There's a quite interesting critical state model that Aaron developed to understand this data, which suggests that essentially they can see the point when they see a vortex enter the crystal. So by extrapolating this data. I know the Los Alamos group has a slightly different interpretation of this, but you can look at the data and basically there's a similar effect, right? So you cool in a certain field down to low temperature, turn the field off and measure the Kerr effect. And there's sort of a remnant Kerr effect that's set by the training of this field. So interpretations aside, at least the data more or less is consistent. And then, what's happening between these two spontaneous or true zero field cooling experiments, I don't quite know. I think we just need to keep measuring and try to resolve the difference between two nominally similar experiments.
Question?
Yeah.
Do you know whether the Los Alamos group did the Kerr rotation on the original samples, the CVT samples? Did they see a signal there?
Yeah, this is the experiment here.
And I don't see a signal there. Should I?
Right. So as I said, they claim not to see any spontaneous Kerr effect in both types of crystals. Now, granted, these are on their crystals, and what Priscilla tells me is that they have trouble actually making crystals with this technique that show a double transition. And I actually promised to send her some samples so they could reproduce it. So we have to do that. But you can see the TC here is 1.5K or so. Okay, so I think they just need to do more measurements. Okay, band structure. This is another hot topic. How much time do I have, by the way?
Well, you've been going since what, about 5 to the hour. So normally we would give you another half hour and then questions.
Okay. Well, I'm not going to be that long, so.
Okay.
Okay, so another hot topic is the band structure, and for obvious reasons, we need to understand how the electrons are situated in this material. And from early on, there's been a bit of discrepancy in the ARPES data. I'm a big fan of Andrew Ray, and I trust his work far above some other groups, but nevertheless, it was really nice to see that the early ARPES data showed some semblance of the calculated band structure, in particular showing these quasi 1D sheets that are shown by the red and blue lines here, the calculation. And so Just to note that this band structure, if you calculate DFT for uranium ditelluride, with localized F electrons and no U, you actually don't get any Fermi surface. You get insulator. So you actually have to turn up U to 1 eV or something like that, or maybe 2 eV to actually get a Fermi surface, and then you get something like this. So the other thing to note is that these states that were observed are actually of the P and D states of the tellurium and uranium. So they're of the light electron states in this experiment, at least. And so the question was, where is the F weight? Andrew's group did actually see this so-called Z pocket situated at the top of the brane zone, which seemed to have some F weight to it. And this is they claimed was a more 3D type pocket. And so, okay, and so goes the controversy. So at least in the beginning, when we did our transport and isotropy study, we seemed to be able to understand it in the context of a sort of 2-band model, giving a 3-dimensional component of conductivity plus a 2-dimensional component that seemed to make sense. Of course, there's been some more recent developments, in particular, the ability to measure quantum oscillations, first seen by the Aoki group in the salt flux crystals, and by a few other groups now, of course. And so the really interesting thing to me is that the observed frequencies more or less match the calculated band structure. There's some quibbles about what fits and what doesn't fit here, which is the band structure of light electrons, but nevertheless, there's a very heavy mass observed through the Lifshitz-Kossovich analysis. And so there's been lots of discussion about how we understand the F weight in this band structure, and whether there's a need for another additional piece of Fermi surface that's not observed, for instance. Okay. Now there is still ongoing experiments, and I would say there's a bit of a fight right now in understanding the quantum oscillations measurements. So the RAND group at St. Louis has claimed to observe, for instance, okay, so they more or less reproduce these kinds of experiments. They were measured by the Aoki group, but they also see these low frequency oscillations that seem to be flat with angle, suggesting this is a 3D pocket. And so the claim in this work was that they do see this 3D pocket. Okay. And then more work by the Cambridge group has a different interpretation. So they also see, at least through some angle range, I'm sorry, I'm not sure if I'm pointing to the right data here. They do, at least I know, they do see through some angle range these small pockets, but they claim that the data is more consistent with a breakdown model where there's some orbits that jump across the calculated Fermi surface. Okay, I'm not an expert here, so I won't decide one or the other. I think it's a good question. Is there an additional piece of Fermi surface? I would claim, at least from my perspective, that the transport data is quite interesting. Not just that it's anisotropic, but it's qualitatively anisotropic. And that I think needs to be answered in this context. Okay, moving on. Next controversy: neutron scattering. Okay, so neutron scattering, at least to date, there's 3 groups that have done inelastic neutron scattering, and I would say that they all their data essentially agrees in the sense that they see some intensity along the Brion zone edge, which is along the B-axis edge. So you see here, and then it's a question of interpretation. Okay, so the simplest interpretation is that if you see some intensity, you assign it to a Q vector, which would imply that there's a propensity towards antiferromagnetic order, and Pencheng Dice group took this and also observed a resonance below the superconducting state transition and implied that this Q vector, finite Q vector resonance was consistent with a antiferromagnetic spin fluctuation driving superconductivity in UTe2, which is interesting in the sense that there's no other known triplet superconductor that seems to be driven by antiferromagnetic fluctuations. Okay. Now, on the flip side, my colleague Nick has a different interpretation of this, and in particular, they just they note that you can see the evolution of the spectrum from high temperature. In fact, so it evolves from where the Kondo lattice state turns on all the way down, and it sort of goes right through TC. And he claims it's more consistent with possibly interband transitions to do with the Kondo state that forms. And so this, of course, needs more work, and I know that there's some work going on to understand this picture. But if this is true, then you don't just necessarily assign a Q vector to the intensity. You have to understand what the intensity is about. Okay. Okay, USR. So next study, and this has to do with spin fluctuations as well. So the early work, which was when we were collaborating with Jeff Saulnier's group, in the first generation of samples, we saw a very, very large muon spin relaxation rate upon cooling. And it was large enough that it was very hard to see what, if anything, was happening in TC. So this question about whether there is a time reversal breaking signature in USR was impossible to answer. Interestingly, if you fit the relaxation rate to a spin fluctuation theory, you actually get something consistent with the ferromagnetic incipient ferromagnetic critical point scenario. And so that was the first observations. And also note that there was two relaxation rates that came out of the analysis of the data, which we didn't quite understand at the time. In the next generation of experiments, which sort of included both lower TC samples and higher TC samples from the Los Alamos group, this was a similar picture, except now the MuSR data allowed Jeff to resolve an oscillation at the lowest temperatures. And so this actually pointed to stopping short of calling it an ordered state, but a spin frozen state at the lowest temperature, which onset around 300 millikelvin. Okay. So this was quite consistent actually with the observations of heat capacity, where there's an upturn at the lowest temperatures. And we thought, well, okay, this makes sense. There's some magnetic clusters that form in the material, and they actually show some perhaps localized magnetic order. Now, what that has to do with TC and so on is an open question. But you can see even in this data that there is some peak in some of the data in the relaxation rate near TC. And so this was never actually understood. Now, and I should note that this was seen in both, samples that had a larger residual heat capacity and a very small residual heat capacity. Now, the latest experiments use salt flux crystals from the Los Alamos group, and they claim to see a much lower spin relaxation rate, and also nothing that happens through TC. Okay, so these are three different papers, three different results, and it's not really easy to say how they relate to each other. I have my own speculations about what's happening, which may have to do with uranium vacancies and so on, but I'll save that for discussion. Okay. All right, so moving on, reentrant superconductivity was observed also very early on, and so we kind of saw it in our first experiments with upper critical field, just going up to the highest fields we could measure in the lab. And then quickly followed up by the Grenoble group where they actually saw if they tilted the field a little bit away, they could actually see this reentrant behavior for fields along the b-axis. And of course, this has evolved with higher TC samples and more elaborate phase diagrams. But at the time, this was sort of the most interesting thing, that there was a reentrant phase that pointed to a second superconducting phase at high field that was abruptly cut off by this field polarized phase, which is a first order transition. You can see some of the raw data here, the first order transition. And then let's see, so there's more recent data which sort of shows the evolution of this phase diagram for b-axis field with higher TC samples, and you can still see that there's basically the same kind of shape. As you can imagine, the upper critical fields just increase with TC, but there's still this bending back feature that suggests there's a second phase here. And there's also some observation of a subtle feature in heat capacity that suggests there's a transition between these two. But I think that's also open field to try to measure the actual transition between these superconducting phases. And of course, do some measurement that would tell you something about the gap structure and symmetry as you go through this putative transition. But that's not done yet. Okay, so this well-known phase diagram from Sheng's work early on at Tallahassee also discovered this high field reentrant phase up in pulse field regime. It's just slightly observable in Tallahassee fields of 45 Tesla, but you really have to go to higher fields to see it properly. And this has been since refined. So this was the first measurements of resistance, and there's some TDO measurements, but there's been magnetocaloric experiments at Los Alamos that are consistent with this being a bulk superconducting state. So it's hard to do other experiments up here, but we're trying to think of other ways to probe that state, to probe the superconducting state up here. It's at this obscure angle here that seems to be about 30 degrees or so, which doesn't seem to point in any particular direction, especially because of the width of this. And it's been shown that this also survives as you increase the base TC. So increasing the base TC with salt flux crystals increases the upper critical field of the low field phase and widens this phase as well. And you can see that this SC3 phase seems to be still consistent here. Okay, so let me see here. So one thing I want to point out, and this is from Nick's group, there's something very unusual here, and this goes back to my comment about the triple R's of samples. So just to point out here, this is from Corey's talk. A sample with a triple R of 64 with TC of about 1.9 K is right here, and this is the boundary of the superconductivity in this high field phase. And then there's a triple R of about 9, so that's about a factor of 7 lower with a TC that's about the same and slightly decreased boundary. But just by looking at these two samples, how could the triple R's be so different? And you still see essentially the same superconductivity. So, of course, it's hard to do systematics of this, even at ambient conditions, low field, and so on. But we're trying to do that to understand. But one of the more exciting results from this study was that this triple R of 7, so almost the same, but this sample doesn't show any superconducting state resistively, and it's still at low field, but it still shows this phase in this high field regime. So that this was deemed the orphan phase. I press to call it the entrant phase instead of orphan, but nevertheless. So this is quite interesting because it says that even if you don't have a superconducting state at 0 field, you can induce it by cranking the field up to 40 Tesla. And again, I think this needs to be studied as a systematic function of triple R and so on, sample quality. But at least in a sample that has no superconducting state, it's still there. Right, so there's some quantitative questions, for instance, this region does seem to shrink a little bit, so is it just a matter of amplitudes? Or is there something really special about this phase here? It's more immune to pair breaking than the zero field phase. Quite unusual, nonetheless. Okay, and then also very recent from Nick's group, they studied the angle dependence of this Lazarus phase as you tilt the field away from this BC plane. And you can see that it's not just limited to this plane. In fact, there's some region that extends far out, showing that the superconductivity actually can persist to even higher fields. Okay, so one thing to note about this, and if you look in this paper for more details, you can find there's some work by Andrei Nevedomsky, just a simple model, trying to understand the implications of this, the shape of this superconducting phase. And one thing to note is that this is non-monotonic, of course. So you can see over here, for instance, this upper critical field goes up and then actually comes down. And this is actually quite hard to understand just from a free energy model for a single component order frame. So just to note in passing that if you can look at this paper for more details, this already implies that this phase perhaps may be a multi-component order parameter phase. And then, of course, as you tilt the field away, there's even more interesting sharp features that evolve that probably need even more complicated explanation. Okay. Regarding the gap structure, we've been continuing to study this. We did a really nice experiment with Brad Ramshaw's group at Cornell to study the ultrasound evolution through TC. And we did a very careful study of different samples, in particular, samples that showed a single superconducting transition and samples that showed a double superconducting transition. And the great work by Florian and company, they were actually able to measure this double transition with ultrasound. So this is C33 going through TC, and you can see in sample S3 that there's this jog here. And that's consistent with the heat capacity data. So the question was, and if you compare these samples, was there a jump in the shear lattice constants or not in either of the samples, which would indicate whether you had a multi-component order frame. And you can see, right here, here's the data. Here's the shear lattice constants, and there doesn't seem to be any jump in either sample. So you can see the jumps. There's kinks in C55 and C66, but there's no jump. So that led us to conclude that the order parameter, at least in zero field at ambient pressure, is a single component order frame. Now, interestingly, C44 shows nothing through this transition. And that's quite unusual. And I would say there's maybe leaves some room for interpretation of this, but nonetheless, why it doesn't respond at all is a good question. Now, I'm sorry. Yeah, one more note about that. So if you look at Florian's paper, there's an added discussion about comparing the amplitudes of the compressive jumps in elastic constants. And there's an argument for a B2U order parameter, which would be nodes along the B axis direction. Just based on the amplitudes of these, but there's other experiments, and I'll show a table at the end of the talk that compares all these things. So I think this needs to be put in context and understood more carefully. So on to thermal transport, and this is another study we did early on, which suggested that the superconducting state definitely had a point node gap structure of some sort. So these are two samples. We measured currents along A and B direction, heat currents, and you can see that in both cases, the zero magnetic field, zero temperature extrapolated data pointed to zero, but had a rapid rise with temperature and a rapid rise with magnetic field, which was consistent with nodal excitations. And just, so this is the blue and red data here, which rise with magnetic field, unlike fully gapped superconductors such as niobium, classic activated type behavior with magnetic field at zero temperature. So that led us to conclude that there's a point node gap structure in at least in the first generation of samples. So now with the advent of higher TC samples and so on, of course, the question came up, does this observation sustain? Does it change and so on? And to our surprise, we learned about the Matsuda group doing this experiment on highest TC samples with the conclusion of a fully gapped state. Okay, so I have some comments about this because I'm an expert in thermal transport, and we also did these experiments at the same time. So first of all, the conclusion is based mainly on this magnetic field dependence shown in red here of the extrapolated thermal conductivity to zero temperature as a function of magnetic field. So the claim is that if you extrapolate this data, it goes to zero and it rises very slowly with field. In fact, doesn't rise at all until you get to something like, a quarter of HC2. Okay, so I'll leave it up to you to decide how you would extrapolate this data because there's no extrapolations given in the paper. And that I just note that the data doesn't go below about 100 and something millikelvin. Okay, so you have to imagine what's happening below that. But luckily we were doing the same experiments, and I'll show you the results of that. But first of all, I just want to point out that it's not unusual to have a very flat, very slow rise in thermal transport at zero temperature as a function of magnetic field. And so this was pointed out early on in theory by Ilya Vector and company in the context of the cuprates, where depending on the parameters, you can see that there's a very slow rise of the normalized thermal conductivity until you get very close to upper critical field, and then it jumps up. And in fact, I have data here, which we actually haven't published yet, but it's on potassium iron arsenic, which is an extremely clean system, triple R 4000, TC of about, I forget now, a few Kelvin. Sorry, 3 in a bit Kelvin. And you can see here, now this is what's believed to be a D-wave superconductor, which has line nodes, so that the zero field value is expected to be a bit different than a P wave or a point node superconductor, I should say. So it actually has a finite value, which is consistent with the line node superconductor. But you can see that the evolution with magnetic field is almost flat. Okay, so just to say that if you have an extremely clean superconducting system and you measure the thermal transport, it's not crazy to expect that this field evolution is very flat. And in fact, here it is. This is data we actually measured. All right, so on to our own studies of uranium telluride. So we were also doing this in parallel and using these 2.1 Kelvin TC samples grown by tellurium flux. So this was what I noted before that was pointed out in Ian's paper here, that we did this for the first time, this tellurium flux growth. Similar triple R's as all the other salt flux crystals and so on. It's a very low residual resistivity. So this is quite exciting because this allows us to do very careful experiments of thermal transport. So you can see there's a nice signature at TC, big rise in thermal conductivity. And so now if we look at the low temperature behavior, we can see how this evolves. So first of all, in this paper that we posted, we actually do a comparison from the first generation samples to the intermediate generation, which means TC, which is higher but still grown by vapor transport, up to the 2.1 Kelvin TC samples. And so first off the bat, if you look at the zero magnetic field extrapolations of the temperature dependence, they all point to zero. And this is consistent with a clean point node system, which is what we said from the beginning, that this zero residual fermionic component is consistent with a point node gap structure. And then what the next question is how does this evolve with magnetic field? And that allows you to discern between different scenarios for the gap structure. So here's 3 samples comparison. You can see the TCs are different, 1.82 and 2.1. Triple R's are different. And you can see that there is, in all cases, a very rapid rise in the residual term as a function of field. And what we're very proud of is in this highest TC sample, we were able to get the experiment down to 30 millikelvin. And to keep that as a function of magnetic field. And you can see here that the extrapolations are very trustworthy from the lowest temperature data. And if you note that, if you look at the data below 100 millikelvin, there is quite a bit of curvature. So you really have to do this experiment to the lowest temperatures to understand what's happening. So then if you take these extrapolations and plot them as a magnetic field, and here we just do it as normalized to normalized HC2 in low field regime, and just as raw data, you can see that there's a rapid rise at low fields for all the samples, including the highest TC sample. So what I would argue is that this data that we measured, especially in this sample here, is within the error bars of the Matsuda experiment. But we clearly show that there's a rapid rise and that it is a nodal superconductor. Okay, there's more interesting things, and I won't go into that, but for instance, if you look at the intermediate field regime, there's actually a interesting peak here. I think I show it. Yeah, I show it here. Okay, so just to show that this highest TC sample, that if you put a large error bar, of course you can call this a 0, but in fact it's not. There's a rapid rise, and this is consistent with the so-called Bolovic effect to do with the shift in the energy spectrum for nodal excitations. But there's this maximum that turns over, and we're still studying what this maximum is about. We believe it's a crossover from the rapid rise due to Bolovic effect over towards a mixed state vortex regime, but we're not sure about that. Okay, so finally, yes, is this a topological superconductor? Well, probably depends on who you talk to, even theoretically. But what I believe certainly is that it's a point node superconductor, and it's of the BU variety. And that implies that there's likely some projected surface states. And this has some implications for some of the experiments I went through, in particular, penetration depth in NMR experiments, as well as other surface sensitive experiments. And I know Seamus gave a talk already delving into this quite deeply about STM and understanding the observations of the QPI structure on the surface being consistent with this kind of picture. So I think that's beautiful work, and I agree with a lot of the conclusions there. I think the jury's still out on settling on the bulk states, for instance. What is the particular order parameter? And I would even argue that this 1 component versus 2 component is an open question. In particular, first, because we all know that as you apply about 1 kilobar of pressure, this superconducting state splits into 2. And that certainly has to be a 2 component order parameter. So how close or how far do you have to be from that 2 component state to claim that it is definitely only single component? Or is there some sensitivity to something in the crystals, disorder, vacancies, etc., that may actually give you localized 2 component behavior? And for instance, even time reversal break. I don't quite know. So nevertheless, this is the current state of all these different experiments and so on. This is from Brad's group comparing the ultrasound to these things. And of course, he concludes that it's V2U based on some arguments. But I think this still needs to be resolved with further experiments. And that's it. So just to cap this overview from start to finish, this is quite an interesting superconductor. There's many experiments to do. There's many experiments that have been done, but doing all the experiments on all the superconducting phases is going to take a while, even though there's a lot of consistency among groups. And I think it's really fun and exciting to work on this material and to collaborate with all these different people and in a fairly friendly community. So thanks for your time, and I'm happy to answer more questions.
Hey, they're clapping for you.
Let's see how we can do this. Let's see if we can keep the questions live. Questions from the audience. Yeah, Seamus.
So several people asked me today why there are no phase sensitive experiments as to the symmetry of the order parameter. Do you know the answer to that, JohnPierre?
I think it's the same answer as in every superconducting, unconventional superconductor. It's just harder to do those experiments. So when Rick and I wrote this review on the iron superconductors, it was the same conclusion, that there was lots of amplitude sensitive measurements and not many phase sensitive experiments. And I think that's still the case. So there's certainly people trying, like yourself. Also, you know, we're trying to do some phase sensitive experiments. It just takes time. I think that's one answer. It just takes time to try to make tunnel junctions and things like that. It would be great to make squid structures and Josephson. But so far, there's only a few reports, and I would say I don't agree with the one that's been posted, but nevertheless, it's just taking time, right? And you know, I saw the part of your talk where you mentioned that if there's a topological surface state present, it's not clear how you would do a Josephson experiment.
Right.
I agree with that completely, and I think that's going to be a challenge. It'll be an interesting challenge, and it'll be a fun challenge, but I think it'll be a challenge.
Other questions? Yeah, Yoma.
So is there anything other than resistivity to show that high field phase is a superconductor?
Yes, I don't have it handy here, but there is an experiment from Los Alamos where they did they measured the magnetocaloric effect. Okay, so it's not heat capacity, but it's not bad. And the issue is that magnetocaloric effect can be sensitive to different things, for instance, vortex physics. But the paper by John Singleton suggests that the up and down, the history dependent evolution of the magnetocaloric signal is consistent with a vortex state. And it's a bulk experiment, so they claim that this is consistent with the bulk superconducting state up here. If you're talking about this phase.
Other questions? You don't by any chance have that resistance data to show us the resistivity at high fields to see if there's a condo-ish like thing going on?
No, I don't. I'd have to dig that up.
I mean, presumably for the polarized paramagnet, there can't possibly be any condo effect. The spins are all polarized in one direction, you think. I don't know.
Yeah, so I'm not aware of I have to look. I know that there's the paper by the Grenoble group where they actually, so they measure, of course, field sweeps at different temperatures, but then they actually plot the temperature dependence at fixed field of the data, and that's where you can see the evolution of this condo
I see.
maximum. But I'm not sure they show that up to the polarized phase. Maybe they do, but I would have to look. You know, the polarized phase, it has an interesting temperature evolution, just to make sure you're aware of that. So it's very sharp for sort of transition at low temperature, but as you warm up, that kind of smears out, and by about 20 Kelvin, which is believed to be the onset, it's almost gone. You know, for instance, if you measure a magnetic signal or transport.
Okay, thank you. So presumably above 20 Kelvin, the condo might switch on, but you might think it would switch off below 20 Kelvin.
Yeah,
Right.
so if I remember correctly, if you're above 20 Kelvin, you will see some feature that's akin to a condo coherence onset, but that's not necessarily in this polarized or ordered phase anymore. It's in a no man's land of
Okay.
polarized spins. Yeah.
Any other questions from the audience? We could see if there's anyone on the chat has a question. Any questions from the chat?
We don't see any.
None there.
I have just one.
Oh,
small
Yoa has another question.
Yeah, so when you started the story about the two, the tails of the two crystals, I think you didn't finish explaining about the resistivity difference of the two different crystals. Can you
Oh,
tell us
uh,
that? For those who have not studied this material?
yeah, sure.
No.
Okay, so do you mean
Oh, I think you need to go towards higher number slides, I think.
so do you mean the residual resistivity, or do you mean the temperature?
The temperature dependence. I think it was different. It looked different.
Okay, well,
When Pierce asked the question, then you kind of skipped the explanation. I think you jumped to the next slide.
sorry, I don't. So at least the temperature dependence, what I was saying before was that there's not much difference at higher temperatures. It really, you see a lot of difference at the lowest temperatures, and this
Another slide was it was another slide. Maybe it was later.
This ABC axis
Yes,
resistivity,
that's
maybe
right.
that was the one that
Yes,
Johan's
yes.
talking about.
Oh, so you mean oops, sorry.
Good question. Good.
Slides are a little slow in this mode. You mean this data?
Yes, so because they're different on the two samples. You didn't explain it. I think you just moved on.
So the question is,
I-
why are these different?
If I look at the left sample data and the right sample data, for me looks different.
This is the same.
Oh, I see. It's you plot it in a different way.
Yeah, this is at low temperatures. This is just to show that we see T squared in all three directions. But there's a bit of a flip of the order actually. So you see that the A-axis resistivity seems to be lowest at low temperatures. Well, sorry, B and C kind of flip orders, but that's not a strong statement because B and C show qualitatively different behavior. So
Yeah, Manu has a question. Manu Brando.
I don't know if it's relevant at all, but I wonder whether the crystal fields of the uranium is known and also the behavior in magnetic fields. Is there any?
yeah, so crystal fields in uranium compounds are notoriously difficult to measure. In fact, I'm not even aware of any compounds. But there's been I think some calculations, but no measurements. So it's not known.
Do you have any thoughts on what's causing that remarkable peak in the row C?
I do. So I think we still believe that it's consistent with some kind of onset of short range magnetic order, or at least some kind of magnetic correlation. And meaning that perhaps, one imagines that rho C would actually, keep going up and be non-metallic at low temperatures. If it weren't for the onset of this correlation. And so where that comes from is there's other experiments that show some feature at the same temperature of about 15 Kelvin. In our paper in particular, I don't have the data here, but if you look at the magnetization and the magnetoresistance, it all seems to point to sort of an onset of higher magnetic sensitivity at that temperature.
And why would that selectively affect the C axis and not affect this B and the A axis?
Well, that's precisely my point as to I'm trying to understand the band structure. If it's all the same Fermi surface, I don't quite understand how you would get this selective response without some fine-tuned model. But
Or some quasi one-dimensional physics, perhaps?
that would be interesting, yeah. And we certainly have some other interesting data that we don't quite understand that shows some onset of anomalous behavior at this temperature, but I'm not willing to talk about it.
Okay. Any more questions? AJP, thank you so much for joining us today.
All right, thank you. Appreciate it.
We'll get some time to belong to this in future.
All right.
Cheers,
thanks.
bye.
Thanks, everyone.
Thank you.
What did he say at the end there?